Hello, this is just a brief demo video from my part of the senior design project, which is called Parts Inventory Display Team 1. I'd like to start with just some cursory concept overview and a brief look at code before a live demo at the end of the video of the project in action. Our project had two Raspberry Pis. We had one Raspberry Pi just kind of handling the graphical user interface that would send signals to the other Raspberry Pi, which controlled the LEDs on the parts inventory shelves. Most of the code that I wrote was for the LED controller Raspberry Pi. So this is just a flowchart that I wrote up, just kind of graphically depicting what the code does. So my code has two threads. In Python, threads can be interesting because of the global interpreter lock, which basically just means that the interpreter for Python runs in only one thread, so quite literally means that your code can only work on one thread at a time. These threads, do not work concurrently. They're non-concurrent. So basically, they take turns using the CPU resources. So we'll start with the Flask server thread. This is the meat of our application. So basically, it goes through, and the Flask server is just sitting and waiting for requests from the kiosk Raspberry Pi, the one with the GUI. And if it doesn't receive a request, it just goes right back, just keeps waiting for requests. If it receives one, however, it's going to send location to the LED software. So this is just going to trigger the software that turns on the LEDs based on the location that it receives, and in the form of an HTTP request, which I'll talk about later. The other thread is what we call our idle mode timer thread. This uses a Python threading timer object. So basically, the gist of this thread is it waits 10 seconds. It just keeps counting over and over until it gets 10 seconds. And if it has not received a request in that time period, it's going to go execute the idle mode animation. If at some point in this 10-second interval we get another request, it's going to reset this timer, and it's going to start, wait another 10 seconds. If it gets a request, it's going to go down here. If it doesn't, it's going to start the process over again. So once we're doing our idle mode, it does not lock our code out. So if we receive a request, it's going to go back, reset the timer, and it's going to go right back in here and send the location to the LED software. If it doesn't receive a request, it's just going to keep continuing to do idle mode. So in order to do our threading timer, we have to set this stop flag because each thread just takes turns sharing the CPU resources. So when we set this flag anywhere in the code, when it switches to the other task, it's going to see that this stop flag is here, and it's going to be able to act based on the value of that stop flag. So we go ahead and initialize our stop flag there, create our timer object, and then start it. This app.run line basically just starts our Flask server. So we initialize that way at the top of our code. We're just initializing it as a Flask application. Very simple. This is our timer thread, the initialization for the timer thread. This is our wait time, which is in tens of milliseconds. So I believe that this should be 10 seconds. So we just have our init statement here, and this is what happens when it runs. So it's just going to go check the stop flag. If the stop flag is true, then it's going to basically reinitialize everything and start over. But if it reaches that 10-second time period and we have not received a request in that time and the flag hasn't changed, then we're just going to go start doing our animation. So this is the meat of our Flask application here. So a Flask application just runs on the static IP address of the device that we are running it on. So since it uses HTTP requests, it's just going to be the IP address of the device colon the gateway slash whatever the rest of the URL is. So slash is just our kind of test case to make sure we're connected. It's not used ever in code. It's just a test case that was left over from development. So this is the case that we usually use. So it'd be IP colon gateway slash transmit. So here we go. When we receive a request and it triggers this receive data function, we're going to set our stop flag so that when it switches to the other timer thread with the CPU, it's going to see that this flag has been set and it's going to reset our timer. And then it waits for the idle thread to acknowledge that we're trying to kill it before moving on. So when we receive a request, as part of the data that should be appended to that request, we're going to get a location in the form of a JSON. So that's all this is doing, is it's grabbing that from the request, and it's going to pass it into function call, which is the equivalent of sending it to the LED software in the diagram here. So I also did briefly some code for the other Raspberry Pi, the kiosk Raspberry Pi with the GUI. Such as this brief overview of this section of the code here. So this is how we send our location string from the GUI Pi to the LED Pi. So it's basically this string here. We're just using HTTP GET request to our IP address that we set for the LED Pi with the gateway slash transmit. So you see that this corresponds to this URL right here. So all it's doing is it's sending this location string in the form of a JSON to this IP address, or this URL, sorry, and then that enables us to turn on the right LEDs on our shelving. Another part of the project that I had the chance to work on was making sure that it would start on startup. For the LED Pi, this was more complicated. So we decided to go with a systemd startup service. I don't want to bore anyone with code because this is all in the setup guide. But we created a one-shot service that basically just triggers Python and triggers our script where it lives on the Raspberry Pi. And this is the line, the center output line, then make sure that we're able to output the request responses. So whenever the Raspberry Pi receives a request, it's going to display the status code and the IP address that of the device that was sending the request. So this script will start it up right on boot for the Raspberry Pi, and it does not require the user to sign in to run or to display to the console. The other Raspberry Pi, we decided it was simplest to just create a icon on the desktop, much like Windows would be. So this is the code for the icon. It's just a .sh file, and all it's doing is it changes to the directory of where our code lives on the Raspberry Pi, and then uses Python 3 with admin privileges, just starts it up. And this step is necessary to make it an executable instead of just a startup script. So now we're going to go to the live demo portion of the video. So now that you've seen the code behind how our parts inventory display works, I just wanted to do a quick demo of the functionality. So one quick thing to note is that this Pi is controlling these LED strips. So when the power goes out or the power comes back on, this Pi just boots right away when it gets connected to power. So it was important to make sure that our code also started on startup. So there is a systemd startup service script that is working behind the scenes here, and is hosting our Flask server. The kiosk Pi would have been difficult to have it start that way, so it's going to boot to this screen, and then once it gets connected to the ports inventory Wi-Fi, you can see there, which is hosted on the other Pi. You go down to this icon that says start GUI.sh, and this is an executable. So we'll hit execute, and now here's our GUI. This Pi sends HTTP GET requests to the Pi on this side of the room that controls the LEDs. So whenever we send a request, one of the cool features is that, so we'll click resistors, quarter watt, and it's lighting up the quarter watt resistors where they live. So we just sent an HTTP GET request to this other Pi. So if we go look, we see that we received a request, a GET request, and 200 at the bottom just means that the request was good, that there were no problems. And you'll also notice that the IP address there, 172.16.0.2, that is the IP address of the other Pi. So it's just displaying the requests that it gets that way.